Electric vehicles are delivering such quiet, high-performance results that some industry projections expect them to make their internal combustion counterparts obsolete as early as 2025. To understand this, look at the mechanical limitations of a standard engine. Its entire architecture is built around linear motion, pistons firing vertically. Converting that repetitive vertical energy into continuous rotation at the crankshaft creates significant mechanical balancing issues that engineers try to mask. This graph shows another constraint. The gas engine only produces usable power within a very narrow speed range. To compensate, cars require a complex, heavy multi-gear transmission that must constantly shift gears to keep the engine within its limited power band during acceleration. Achieving superior performance isn't about making a more efficient gas engine. It's about removing this entire layer of mechanical complexity. The foundation of this shift is an invention made by Nikola Tesla over 100 years ago, the induction motor. This motor is defined by its physical simplicity. It functions without brushes, permanent magnets, or a single moving piston. A three-phase alternating current is fed into the outer coils, creating a rotating magnetic field. This induces a current in the inner rotor, pulling it into a spin. The motor produces direct rotational motion, constantly chasing the magnetic field. Because this system provides uniform power from 0 all the way to 18,000 RPM, the power band looks like this, a flat, consistent line across almost the entire operating range. This massive speed range eliminates the need for complex shifting. Instead of a multi-gear transmission, the car can utilize a simple single-speed gearbox. The induction motor achieves superior performance because it reduces the number of moving parts sitting between the energy source and the wheels. Powering this motor requires a massive battery pack, which is integrated directly into the floor of the vehicle. Rather than using one large monolithic cell, this pack is composed of approximately 7,000 small lithium-ion cells. This cellular design allows glycol coolant to flow through the gaps between each cell. This prevents thermal hotspots and ensures an even temperature distribution, which extends the total life of the battery. Placing this flat, heavy architecture at the base of the car lowers the center of gravity and increases the vehicle's structural rigidity against side collisions. However, there is a mismatch in power types. The battery produces DC power, but the induction motor requires AC power to generate its magnetic field. The inverter solves this. It acts as the brain of the car, converting the battery's DC into AC, while dictating the motor's speed by instantly adjusting the AC frequency. This digital control replaces heavy traction hardware. While a traditional car might use a heavy, limited-slip differential, this car uses a rugged, open differential. If sensors detect a wheel slipping, the inverter simply cuts the electrical power to that wheel with millisecond precision. The combination of the battery and inverter demonstrates that utilizing smart electronic software is more effective than relying on heavy mechanical hardware. This simplified digital ecosystem enables a unique driving experience, the ability to control most of the vehicle's motion with just a single pedal. It's made possible through regenerative braking. Instead of wasting the car's kinetic energy as friction heat in the brake pads, the system recovers that energy and stores it as electricity. This diagram shows the moment the driver releases the accelerator. The inverter drops the frequency of the magnetic field, forcing it to spin slower than the physical rotor. This speed mismatch turns the induction motor into an electrical generator. The wheels are now driving the motor, rather than the other way around. As electricity flows back into the battery, an opposing electromagnetic force acts on the rotor. This physically slows the wheels down, allowing the driver to modulate the car's speed with extreme precision. Traditional friction brakes are still available for a complete stop, but the vast majority of your driving speed is managed through software and magnetic fields. The Tesla Model S recently became the world's fastest accelerating production car by completely stripping away mechanical resistance. By replacing clunky gears and physical traction systems with responsive inverters and software, the electric vehicle suggests the future of mechanical engineering is digital.